I'm going to break this into a couple of pieces. First things first, I'm going to give you a list of steps that's not going to mean anything at all right now. Okay? So this is for the simplex method, which is a little bit like that geometrical optimization dealie, but there's this problem with like when there's more variables than 2, you're kind of in a like weird high dimensional space, and finding vertices is like awkward, maybe impossible, right? That was a little polygon we passed around last time. So the steps for this are 1, make equations. This is not different. Okay? Okay? Right? Yes? Make the same equations you did last time. Step 2. Put in slack variables. This doesn't mean anything right now. Just trust me, you should do this. Okay. Step 3 is going to be make a table. That's going to look a little bit like an augmented matrix. So you might actually think augmented matrix here. Some of the tricks are actually the same. Some of the objects are a little bit different. But you can really look at that thing and think about an augmented matrix. Step 4 is going to be find the biggest payoff. Step 5 is going to be find the constraining constraint. That sounds a bit bizarre too. Trust me, this will make sense. I'm going to talk a lot about the constraining constraint in here. What that is the most constrictive or the most restrictive restriction, right? So which of these things are you going to run into first, basically? And then step 6 is going to be this thing about pivot operations. And again, on this one, you're going to think about an augmented matrix. Cool? I don't know if this makes sense. No, sorry, I keep asking. And number 7 is going to be check for a payoff. Right? And then if there is one, go back to step 4. You guys cool with us? If there isn't one, what are you?
Done.
Hopefully done. You guys see that?
If you don't find a payoff on step 4, you continue.
If you don't find a payoff at all on step 4, you can be done with the problem.
Okay.
That will never happen.
Okay.
Otherwise, why are you making the problem?
That'll happen when there's only one way to do the thing you've described.
Yeah.
So this would be, there's only one vertex, which would be a little bit bizarre, but could happen.
Mm-hmm.
Like you could write down some equations that only intersect at one point, right? And so maybe that would be this, like, oh, there isn't a payoff, but that would be super bizarre. Okay, and what this thing is actually doing, I want to give you a like kind of intuitive thing. So maybe here's some feasibility polygon, right?
Mm-hmm.
And so what I'm going to do is I'm going to start at a vertex, right? Usually the 0, 0 vertex. And then I'm going to say, okay, in which direction, right, going this way or going that way, am I going to get the best payoff? And then I'm going to go that way. You guys see this? So we're going to say, okay, the biggest payoff is kind of in this direction. So I'm going to ignore that arrow. I'm going to go this way. Now I'm here. We're going to run through all of this stuff and figure out what sitting there looks like. Then we're going to check for another bigger payoff. And we're going to wonder, is it better for me to go that way or possibly another direction? You guys see I don't have 3 dimensions here, so it's a little hard to show the or possibly another direction. But that's the idea. You're going to pick one. You're going to wander that way. Right? So maybe we end up down here. Then we're going to wonder, is there a bigger payoff from there? Well, what it looks like when there isn't is that the other way came in that same direction. There isn't a way I can go from here to get a bigger payoff. That's really what this thing does. So it kind of wanders around, going from vertex to vertex, asking, is there a way for me to get better than the spot I'm at? You guys see that? And there's some really deep geometry stuff that says that you can't actually end up at a spot where this will stop that's not the end. That's a really big ask right now, because it's pretty easy to imagine in your head, like, you know, maybe a polygon that looks like this or something, and I'm just asking how far am I from 0, right? Like maybe, if I were out here, I'd have to go back towards 0 to make any progress further away. That can't happen in this linear programming model. There's a good reason for that, but it's kind of deep.
If you're always walking uphill, you'll end up at the top.
Yeah, exactly. And for some reason, that has to happen here. There has to always be once you've walked uphill, you get to the end. Okay? And you get to the right end. Cool? That's a big ask for right now, but it's true. So put these down someplace because we're going to use them for that example.